Hello physics students, this is Mrs. Buchanan. In this lesson we're going to dive much deeper into Newton's law, first law of motion, which is inertia. And we need to revisit our big idea, which is forces cause changes in motion. And we're going to take a look at our learning objective, and this is learning objective number 4, which is to discuss Newton's first law of motion. The first thing I want you to do, though, is I want you to do some practice problems, and I'm going to give you a little bit of background on this. We're going to be measuring force using the Newton, and the Newton, of course, was named after Isaac Newton. So, a little bit of information. 1 unit of force causes 1 kilogram of mass to accelerate at 1 meter per second squared. Because force is equal to mass times acceleration, capital F equals ma, one force unit has the dimensions 1 kilogram times meters per second squared. The unit of force in the International System of Units is called the Newton. Please stop this video and do the 5 practice problems on your questions. Now we will be going to our learning objective number 4, and this is discuss Newton's first law of motion. In order to understand Newton, we have to go back and we have to take a little bit of information on Galileo, because he pretty much set the stage for Newton. What is the motion of an object with no net force on it? Think of a ball rolling on a surface. How long will the ball continue to roll? That depends on the quality of the surface. If you roll it on a thick carpet or soft sand, it will quickly come to rest. If you roll it on a surface that is hard and smooth, such as a bowling alley, the ball will roll for a long time with little change in velocity. You can imagine that if all friction were eliminated, the ball might roll at the same velocity forever. Galileo did many experiments on the motion of balls on very smooth surfaces. He concluded that in the ideal case, horizontal motion was eternal. It would never stop. Galileo was the first to recognize that the general principles of motion could be found only by extrapolating experimental results to the ideal case, in which there is no friction or other drag force. So let's talk a little bit about Newton. He did generalize Galileo's results to motion in any direction. Now, when we talk about Newton, Newton was a British physicist and a mathematician. On Christmas Day in the year 1642, the year that Galileo died, Isaac Newton was born prematurely and barely survived. Newton's birthplace was his mother's farmhouse in Woolsthorpe, England. His father died several months before his birth, and Isaac grew up under the care of his mother and grandmother. As a child, he showed no particular signs of brightness, and at the age of 14 he was taken out of school to work on his mother's farm. As a farmer, he was a failure, preferring to read books he borrowed from a neighboring pharmacist. An uncle sensed the scholarly potential in young Isaac and prompted him to study at the University of Cambridge, which he did for 5 years, graduating without particular distinction. A plague swept through England, and Newton retreated to his mother's farm, this time to continue his studies. At the farm, when he was 23 and 24 years old, he laid the foundation for the science of physics. Seeing an apple fall to the ground led him to consider the force of gravity extending to the moon and beyond. He formulated the law of universal gravitation, which we'll talk about in a few minutes. He invented the calculus, a very important mathematical tool in science. He extended Galileo's work and developed the 3 fundamental laws of motion. He also formulated a theory of the nature of light and showed, using prisms, that white light is composed of all of the colors of the rainbow. Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. It was his experiments with prisms that first made him famous. When the plague subsided, Newton returned to Cambridge and soon established a reputation for himself as a first-rate mathematician. His mathematics teacher resigned in his favor, and Newton was appointed the Lucasian Professor of Mathematics. He held this post for 28 years. In 1672, he was elected to the Royal Society, where he exhibited the world's first reflector telescope. It can still be seen and preserved at the Library of the Royal Society in London, with the inscription, "The first reflecting telescope invented by Sir Isaac Newton and made with his own hands." It wasn't until Newton was 42 that he began to write one of the greatest scientific books ever written, the Principia Mathematica Philosophiae Naturalis. He wrote the work in Latin and completed it in 18 months. It appeared in print in 1687 and wasn't printed in English until 1729, 2 years after his death. When asked how he was able to make so many discoveries, Newton replied that he solved his problems by continually thinking very hard and long about them, not by sudden insight. At the age of 46, he was elected a member of Parliament. He attended the sessions in Parliament for 2 years and never gave a speech. One day he rose, and the House fell silent to hear the great man. Newton's speech was very brief. He simply requested that a window be closed because of a draft. Although Newton's hair turned gray at 30, it remained long, full, and wavy all of his life. Unlike others in his time, he did not wear a wig. He was a modest man, although very sensitive to criticism. He never married. He remained healthy in his body and mind into old age. At 80, he still had all of his teeth, his eyesight and hearing were sharp, and his mind was alert. In his lifetime, he was regarded by his countrymen as the greatest scientist who ever lived. In 1705, he was knighted by Queen Anne. Newton died at the age of 85 and was buried at Westminster Abbey along with England's great kings and heroes. Newton opened up the universe, showing that the same natural laws that act on Earth govern the larger cosmos as well. For humankind, this led to increased humility, but also to hope, inspiration, because of the evidence of the rational order. Newton ushered in the Age of Reason. His ideas and insights truly changed the world and elevated the human condition. So, Newtonian mechanics is a deeper understanding of the way all objects move and interact with each other. They were the essential elements to explain Earth and space, and again, he invented calculus, the 3 basic laws of motion, and the law of gravitational force. So if we take a look at this law of gravitational force, in 1666, some 45 years after Joseph Kepler did his work, Isaac Newton was living at home. So this was during the time that the plague was occurring in England. Newton had used mathematical arguments to show that if the path of a planet were an ellipse, which was in agreement with Kepler's first law of planetary motion, then the magnitude of the force, F, on the planet resulting from the Sun must vary inversely with the square of the distance between the center of the planet and the center of the Sun, meaning force is proportional to 1 over the distance squared. D is the distance between the centers of the two bodies, so it would be capital F is proportional to 1 over d squared. Newton also showed that the force acted in the direction of the line connecting the centers of the two bodies. But was the force that acted between the planet and the Sun the same force that caused objects to fall to Earth? Newton later wrote that the sight of the falling apple made him think about the problem of the motion of the planets. He recognized that the apple fell straight down because Earth attracted it. He wondered whether this force could extend beyond the trees, to the clouds, to the moon, and everywhere beyond. Could gravity be the force that also attracts the planets to the Sun? Newton hypothesized that the force on the apple must be proportional to its mass. In addition, according to his own third law of motion, the apple would also attract Earth. Thus, the force of attraction also must be proportional to the mass of Earth. This attractive force that exists between all objects is known as gravitational force. Newton was so confident that the laws governing motion on Earth could work anywhere in the universe that he assumed that the same force of attraction would act between any two masses, m sub A and m sub B. He proposed his law of universal gravitation, which is represented by this equation. F equals G, m sub A, m sub B, divided by d squared. In the equation, d is the distance between the centers of the masses, g is a universal constant, one that is the same everywhere. According to his equation, if the mass of a planet near the Sun were doubled, the force of attraction would be doubled. Similarly, if the planet were near a star having twice the mass of the Sun, the force between the two bodies would be twice as great. In addition, if the planet were twice the distance from the Sun, the gravitational force would be only 1/4 as strong. Because the force depends on 1 over d squared, it is called an inverse square law. So you can see that he used these methods on Earth and applied them also to space. So Newton generalized Galileo's results to motion in any direction. He stated an object that is at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant speed, if only the net force acting on that object is zero. This statement is called Newton's first law of motion. It's also called the law of inertia. Inertia is the tendency of an object to resist change. If an object is at rest, it tends to remain at rest. If it's moving at constant velocity, it continues moving at that velocity. Okay? So we talk about equilibrium, which we talked about last chapter. We also talked about free body diagrams, which we will be drawing later on. So, in the absence of forces, a moving object tends to move in a straight line indefinitely. Objects continue to move by themselves. Forces are needed to overcome friction. Forces are needed to set the objects in motion initially. And inertia, again, is the tendency of an object to resist change. So this contradicted Aristotle, because Aristotle believed that you had to have continual forces to maintain motion. If net force is zero, then an object is in equilibrium. We already talked about static, which is at rest, and dynamic, which means it's moving at constant velocity, which is constant speed and direction. Net force disrupts or disturbs equilibrium. Any change in velocity or acceleration is the result of the net force acting on an object. So I want you to copy down this chart. This is the forces that we will be continuing to talk about: friction, normal, and spring. These are all various kinds of forces with their symbols, their definition, and their direction. In the second slide, you see tension, thrust, and weight, and these are those that we have already talked about, as well as some that we will continue to talk about as we move along into the second and third laws of motion, and eventually into aerodynamics. Thank you very much. This concludes lesson number 4 on our chapter of Newton's law of inertia.